Good morning, all. I think we can begin today's webinar by welcoming our resource person. And we have with us our dear principal sister, Maggie Jose. She's a part of our department too. I welcome her wholeheartedly to this webinar. She is a constant source of support in all our activities. I welcome you, sister. And we have our resource person, Dr.Vijitha Mukundan. She is an assistant professor in Department of Mathematics, Sacred Heart College, Chalakudi. She completed a PhD from NIT Calicut, and she will be talking to us on fractional calculus. I welcome all the participants, and our principal sister will say a few words to us. Welcome, sister.
Good morning to all. I am very happy to inform that this year our college is celebrating 75th year of its establishment. As a part of it, each department is conducting a series of webinars. The impact of COVID-19 on all walks of life is unprecedented, and it has a detrimental effect on almost all sectors. No doubt, this is a crucial time for education sector also. Teaching and learning are the core activities of a college. We can try to exploit every moment of this precious time. This is perhaps the most critical moment for all of us. It is imperative for all our education system to rise up to the challenge, and is necessary that our education system provides a proper ecosystem for our students, researchers, and teachers to work and achieve their goals, dreams, and aspirations. With immense pleasure, I congratulate Dr. Pavadi K.S., Head of the Department of Mathematics, and all my dear colleagues of the department for taking efforts to conduct such a webinar on the topic Introduction to Fractional Calculus to cope up with the situation. On behalf of the entire St. Mary's College and Department of Mathematics, I do hereby welcome our distinguished speaker, Dr. Vijitha Mukundan, an expert in this field. I also take this opportunity to welcome our guests, delegates, and students who have joined to grace this occasion. May this initiative prove to be a successful step towards technology enhancement in education. Wishing you all a good time ahead. Let me conclude. Thank you.
Thank you, sister. Participants, please be careful. Please try to mute your video and audio both. And I welcome Dr. Vijitha ma'am to handle the session. Welcome, ma'am.
Thank you, Diana Miss. Good morning, dear sister principal, dear teachers and students. A very good morning to one and all. First of all, I would like to thank the Research and PG Department of St. Mary's College, Thrissur, for giving me an opportunity to deliver this talk. Especially, I would like to thank Parvati teacher for giving me such an opportunity. Also, I would like to congratulate the department for taking such an effort during this time of pandemic. I will be give you a brief introduction to the topic fractional calculus. Please check if you are able to see the slides.
No, ma'am. Yeah, no, it's.
So the slides are
No,
visible
madam,
to all.
please share the screen. It's not visible.
Yes. Now it's visible. Now it's
Is
visible.
it fine?
Yes, ma'am.
Okay, so we will start now. So this is the outline of my talk. First, I will give an introduction to the topic fractional calculus, and then it will be followed by some historical developments. And then I will give some definitions of fractional derivatives and integrals. And it will be followed by the very famous definition of Riemann-Liouville fractional integral and derivative and Capiccio fractional derivative. And then it will be followed by some examples. So let us look at the topic of the class, that is fractional calculus. Have you ever heard this name before? What is the meaning of this term? Actually, it is a misnomer, a term that is misleading. That is, it is not in accordance with its real meaning, just like the term natural numbers and real numbers. So have you ever thought that does natural numbers occur naturally? Even if we call it natural numbers, does it occur naturally? Same with the case of real numbers. Does real numbers occur in reality? As the name suggests, but it is in contradiction. Even though they depict some physical quantities, but they does not occur in reality. Now, let us look at the topic fractional calculus. Now, this topic is also a misnomer. It does not mean calculus of fractions. Neither it means fraction of any type of calculus that you have already studied. Okay, which type of calculus you have already studied? You know, differential calculus and integral calculus. And of course, the PG students might have studied calculus of variations. So this topic is not related to any one of these topics, which you have already studied. Then what is this fractional calculus? What does this mean? So it is actually the study of integrals and derivatives of arbitrary order. So we already know how to find the first derivative, dy by dx. We are familiar with the second derivative, and similarly we can find the nth order derivative. The same way we know how to integrate, integration, line integral, then we have the double integral, triple integral. Like that we know how to do n times integration. But here all the order is a integer, positive integer. But what happens if this order is arbitrary number? That is, the order is not an integer, it can be a negative fraction or it can be a complex number. So fractional calculus is the study of derivatives and integrals of arbitrary order. So look at this term, that is dy by dx. Here the power is alpha, derivative of y with respect to x, and the order is alpha, where alpha is arbitrary. So here alpha can take any value. It can be a positive value, a negative value, a fraction, or it can even be a complex number. So fractional calculus deals with derivatives and integrals of arbitrary order. So let us see the history and when this term was coined out. Actually, this topic is 300 years old as the ordinary calculus that we study here, when Leibniz and Newton discovered the ordinary calculus. And we will see how the term fractional calculus came. It was a result of a communication between Leibniz and L'Hopital. I will describe it through a video. So I hope everyone was able to view the video. Okay, so it was a result of communication between Leibniz and L'Hopital. So L'Hopital raised the question, what happen if the order will be half? That is, half derivative of any function. Does such a function exist? If it exists, what is its relevance? Where it can be used? What are its application? So as a result of this, many mathematicians worked on it, and mainly earlier this subject was of interest only to mathematicians, and it was not popular among science or engineering community. But recently, in the past few years, it drew attention of several people working in applied fields of engineering, science, economics, bioengineering, and finance. So in this talk, we will study mainly about the fractional derivative of functions. We will see, does it make it any sense of saying of fractional derivative of a function? Or is it just a mathematical fantasy? How it is useful, why we are going for fractional calculus, what is its use, and what are the elementary definition of fractional derivatives and fractional integrals. Now we will use some notation. So the fractional derivative of order alpha will be denoted by this symbol, d, capital D to the power alpha, which is the alpha derivative of the function, where alpha can be integer, fraction, or even a complex number. For example, d to the power n denotes n time differentiation. And we know that integration is antiderivative. So hereafter, d to the power minus n, it represents n times integration. So you need to remember this notation to follow the class. Okay, so d to the power n denotes n times differentiation. And even though here d is written, but the power is minus. So d to the power minus n always represent n times integration. So these notations we will be using. Now the fractional derivative is denoted by this symbol. So here you have d to the power alpha of a function f of t, and here you have two symbols a and t. They are nothing but the bounds of the operation, or what we say limits of the functions. So this is the notation, d to here alpha will be positive, because if alpha is negative, it will represent a fractional integral. Okay, so a fractional integral of order beta is represented like this. So same notation, a, d to the power, here you have minus beta, where beta is positive. A and t are limits of the operation. Here the operation is fractional integration, and here the operation is fractional differentiation. Now combining both terms, fractional differentiation and fractional integration, both are combined in a single term, and that operator is called integro-differential operator. It is represented by this symbol. Here alpha can be positive as well as negative. Now if alpha is positive, it represents the operation fractional differentiation. If alpha equal to 0, it is nothing but the identity function. And if alpha is negative, it represents the operation fractional integration. Okay, so in the previous definition, we have defined what is how we define fractional differentiation. In the same way, fractional integration. Now both the operations are combined in this operator. It is called an integro-differential operator. And the values are like this. If alpha is here, alpha can be positive and negative. So if alpha is positive, it represents the fractional differentiation. If alpha is negative, it represents fractional integration. So I hope the notations are clear to you. Okay. Now next, for studying fractional calculus, some basic functions are required, and one of the such basic function is the gamma function. Gamma function was invented by Euler in 1729. And what is this function? What is the advantage of gamma function? Now, the gamma function generalizes the concept of factorial. For factorial, n factorial is valid only if n is a positive integer. So what about now? When gamma function was introduced, it generalizes the factorial, and now n can be taken the value n can take the value non-integer values and also even a complex number. So that is the advantage of gamma function. So gamma function generalizes the factorial concept, and here we can choose n to be non-integer values and even a complex number. So in this way, the gamma function is defined: integral 0 to infinity t to the power n minus 1 e raised to minus t dt. And these relations we can derive very quickly from the definition of gamma function itself. That is, gamma n plus 1 is n gamma n, and gamma n plus 1 happens to be n factorial. So here, whenever factorial is there, it should be a positive number. And the value of gamma half is root pi. This is a very important result which we will be using often. Now, suppose n is a complex number. So I have just denoted it by z. Then we have the same definition. Gamma z is integral 0 to infinity t power z minus 1 e raised to minus t dt. And this integral will converge when real part of z is positive. That is, it is in the positive half plane. And also this equation is valid. Gamma z plus 1 is z gamma z. So for complex numbers also we can use the gamma function, and that is the benefit of using gamma function, as it generalizes the factorial, and n we are free to take n. N can take any value and it can even be a complex number. Now another function which is as important as gamma function is the beta function. It is also called Euler's integral of the first kind. Now beta function is defined as integral 0 to 1 t to the power x minus 1 minus t to the power y minus 1 dt. Here also x and y can be complex numbers, and the condition is that real part of x and real part of y should be greater than 0. And also we have a relation between beta function and gamma function, which is very beneficial. That is, beta of xy is gamma x gamma y whole divided by gamma of x plus y. Now we will go into the step-by-step method by which the fractional derivative was introduced. So in 1819, Lacroix found the formula for derivative for arbitrary order of monomials. For example, you take f of x to be the function x raised to k. Now its first derivative, ordinary derivative, f dash of x is kx to the power k minus 1. Similarly, the second derivative, f dash of x is k into k minus 1 x to the power k minus 2. Now if you generalize it, take the nth derivative of this function x raised to k. So here in the numerator you will get k into k minus 1 into k minus 2 up to etc. k minus of n minus 1. Now if you supplement k minus n factorial in the numerator and denominator, so that the numerator will become k factorial and the denominator will become k minus n factorial. X to the power k minus n, where k minus n is greater than or equal to 0. Now this is for integer values. Now what Lacroix did is, Lacroix extended it to derivative of arbitrary order by replacing the factorial with the gamma function. Okay, so according to electroics, this is the fractional derivative of a monomial. Fractional derivative of x raised to k is given by gamma k plus 1 by gamma k minus alpha plus 1 x raised to k minus alpha. Here alpha is arbitrary. So how this came? Here k factorial is there, so we have used the corresponding relation between factorial and gamma. Okay, so this is k factorial is gamma k plus 1. Similarly, k minus n factorial is gamma k minus alpha plus 1. Alpha is used to denote arbitrary order. Okay, so electroics found the formula for derivative of arbitrary order for monomials only. Okay. Now, using this formula, many mathematicians tried different possibilities. So, for example, the first question was, what would be the half derivative of x? So, half derivative of x we can calculate using this formula. So, we have, this is the formula developed by electroics. So, here you have to put alpha equal to half and k equal to 1. So, we will get the half derivative of x. So, in this formula, when we substitute, you will get k equal to 1. So, gamma 2 by gamma. Here you put alpha equal to half, k equal to 1. So, we will get gamma 3 by 2, x raised to half. Now, we know by the properties of gamma function, we know gamma 2 is nothing but 1 factorial. So, it is 1. And gamma 3 by 2 is 3 by 2 is a fraction. So, you have to use n minus 1 into gamma n minus 1. So, 3 by 2 will give you 1 by 2 into gamma 1 by 2. And gamma half, you have to remember the value of gamma half. As I said earlier, gamma half is root pi. So, we get here the value is 2 by root pi x raised to half. So, this is the half derivative of x. So, 2 by root pi x raised to half. Now, what does this imply? So, this is the graph of the function half derivative of x. Here, blue line represents the line y equal to x. The red line is the ordinary derivative of x. So, it is 1, constant function 1. And this purple line or the maroon line is the half derivative of x. So, in this way, we will get the, so this is how we plot the half derivative of x. Now, many mathematicians were further curious to find what happens if you take again half derivative of this half derivative of x. Will it give the first derivative of x? That was the main question. So, we have, this is the half derivative of x, 2 by root pi x to the power half. Suppose again we take half derivative of this function. So again we can apply, we can use this formula developed by electroics. So this is the formula. Now we have to find the half derivative of this function. So x raised to half. So we have to take alpha equal to half and k equal to half. K is this power. So when we substitute here, 2 by root pi is a constant. We took it outside, then half derivative of x raised to half. Again, when we applied here, we got gamma 3 by 2 by gamma 1, and this is 0 because half minus half x raised to 0 is 1. So we got gamma 3 by 2. Gamma 3 by 2 is again 1 by 2 into gamma 1 by 2. Gamma 1 by 2 is root pi. So root pi by 2, this will get cancelled. So you will get it is equal to 1. So half derivative of x is nothing but the total derivative, that is the ordinary derivative of x or the integer derivative of x, and which is 1. Now this property is satisfied by the formula, but it is not necessary that all fractional derivatives satisfy all those properties that we have for integer order derivatives. There may be some differences. Now, next important thing is, what is the half derivative of a constant function? We know that in ordinary derivative, when we do, we know half derivative of a constant function is 0. But it is not in the case of a fractional derivative. So when we find, now we will find the fractional derivative of the constant function. So let f of x equal to c. Again, we use the formula developed by Lacroix. So d to the power alpha x raised to k is equal to gamma k plus 1 by gamma k minus alpha plus 1 x raised to k minus alpha. So here alpha is 1 by 2 half derivative and k is 0 because here you have constant function. So it is x raised to 0. So we can write this as c into x raised to 0. Now if we substitute the values in this, what we are getting is c is a constant, gamma 1 by gamma half x raised to minus half, k minus alpha, so it will be minus 1 by 2. Gamma half is root pi again. So what we are getting, half derivative of the constant function is c by square root of pi x. Okay, it is not so surprising because it is not even 0, and you can see in the neighborhood of origin, this function is becoming infinite. As x tends to 0, this function has become infinite, so it is not even close to 0. So this is the half derivative of the constant function. So the fractional derivative need not be same as that of our ordinary derivative that we have studied, and the properties will also be different. Now, in 1822, Fourier found the arbitrary derivative for the sine and cosine function. So it is also a particular case. So suppose, so we don't have a general formula till now. So first we found for a monomial, now for a trigonometric function. So let f of x equal to sine bx. Then similarly, its first derivative f dash of x, we know it is b cos bx. Then again you find second derivative f double dash, so it will be minus b square sine bx. So in that way, if we generalize it, we will get the nth derivative of x is b to the power n sine of bx plus n pi by 2. So if you give n 1, 2, 3, etc., you will get all the ordinary derivatives that we know. Now, what Fourier did is, Fourier found the formula for the arbitrary derivative of sine and cosine. So this is for the arbitrary order alpha. So d to the power alpha sine bx is b to the power alpha sine of bx plus alpha pi by 2. So here alpha can take any value. Now this is applicable for cos also. For cos function also we will get in the same way. Now the different fractional derivatives need not give the same value, because here we have the fractional derivative for sine. Now sine can be written as a power series expansion. You can write it in terms of the monomials. Okay, you can write the power series expansion of sine x. So when we find the fractional derivative of sine x using this formula, and if we find the fractional derivative of sine x using the formula for monomials developed by Lacroix, we find that the answers are not same. There are differences. So there are so many variations are there. All the formulas derived are not so consistent, and we do not have any general formula yet for finding the fractional derivatives. Next is for exponential function. This was given by Liouville. Liouville found the arbitrary derivative for the exponential function. So, so here f of x is equal to exponential of ax. We know its nth derivative will be a power n e raised to ax. Now, if I denote nth derivative by capital D, so d power n e raised to ax equal to a raised to n e raised to ax. So exponential function possesses very nice properties. Okay, mainly due to the fact that they act as the characteristic function for the differential operator. Because if you consider this, This is of the form ax equal to lambda x. Okay, so this is the characteristic value and this is the characteristic function. So exponential function act as the characteristic function for the differential operator. So it possesses many nice properties. But what Liouville did is he also found the arbitrary derivative for the exponential function by replacing n with alpha, where alpha can take any value. That is, derivative of arbitrary order alpha is given as d to the power alpha e raised to ax equal to a raised to alpha e raised to ax. Again, e raised to ax, we know that sine this trigonometric function can be written in terms of the exponential functions. So when we calculated the fractional derivatives using the formula for exponential function, and then we compared it with the formula given by Liouville for the exponential function directly, we found that they are not matching. So there were so many variations were there. Then there were so many developments took in the field of fractional calculus. In 1823, Abel provided first application for fractional calculus was provided by Abel. Then Riemann and Liouville also worked a lot. They studied this subject in depth, but the Riemann's contributions was not acknowledged and it was published only after his death. And in 20th century, Hardy and Littlewood studied many properties of fractional integrals. So actually more than 15 definitions of fractional derivatives and integrals are available. Each of them is mathematically correct and has its own properties and applications. So we have to choose the one which will fit to our research problem or our interest. So each definition will have its own limitations as well as its applications. The most used definitions are the Riemann-Liouville fractional derivative, which is mainly applicable in calculus, and the Capiccio derivative, which is mainly used by physicists and in the field of applied mathematics. So these are the two main definitions given for fractional derivatives. And there are so many definitions are available, but we have to use it according to our research interest or according to our problem. So next we will study about how Riemann, Liouville and Capiccio derived or came to their definition of fractional derivatives and fractional integrals. So first of all, we will see the Cauchy's formula. I think PG students will be familiar with this. How to integrate n times. So given a function f of x, the formula is given by Cauchy for finding the n time integration of this function. So it is given by 1 by n minus 1 factorial integral a to x, x minus t whole raised to n minus 1 f of t dt. This is a formula for finding n-fold integration of a function f of x. Now, if we are finding the fractional integral of order alpha, where alpha is arbitrary, we are simply replacing this factorial with the corresponding gamma function. So, n minus 1 factorial is gamma n. So, if alpha is arbitrary, we are using the symbol alpha. So, since again you see the notation here is d to the power minus alpha. Even though d stands for differentiation, d to the power minus alpha refers integration. Okay, as I told earlier, this is the notation for integration, as integration is antiderivative of differentiation. So d to the power minus alpha f of x. This LHS means alpha times integration of the function f of x. And it is given by the formula 1 by gamma alpha integral a to x, x minus t whole raised to alpha minus 1 f of t dt. Now, this is the formula given by Riemann and Liouville. So this is the definition of the Riemann-Liouville fractional integral. This is a formula for finding fractional integral. So here LHS is d to the power minus alpha. Also we have the limits here. AX, this represent the lower limit and this represent the upper limit. So as I told earlier, A and X are the bounds of the operation. So here the operation is integration. So A and X are limits of integration. So integration is from A to X. D to the power minus alpha represent integration of the function f of x is given by RHS is 1 by gamma of alpha integral A to x, x minus t whole to the power alpha minus 1 f of t dt. So here also we have the condition that real part of alpha is greater than 0. It came from the definition of gamma function. And also x should be greater than or equal to a. So this is the definition of Riemann-Liouville fractional integral. In particular, if the lower limit a is minus infinity, we call it as Liouville fractional integral. And if a is equal to 0, we call it as Riemann fractional integral. So, and if a is arbitrary, it can take any value, then it is called Riemann-Liouville fractional integral. This is one of the integral which is commonly used in calculus. It has its own, some limitations are there, like the derivative of the constant function. Again, if you find Riemann-Liouville fractional integral for constant function, it is not 0. And also some limitations are there. So the next derivative came. Now this is Riemann-Liouville fractional integral. Now next we will see what is Riemann-Liouville fractional derivative. Okay, so Riemann-Liouville fractional derivative is derived from the integral itself. So d to the power alpha f of x. So here d to the power alpha represent differentiation of arbitrary order alpha. Now it is written as, because integral satisfy these properties, okay, so we can split it and write it as n, alpha can be written as n minus n plus alpha. Now d to the power n, here n is an integer, so it represents the nth order derivative. This is the usual derivative which we study in calculus. And here you have d to the power minus n minus alpha. So d to the power minus means it represents integration. So this is integration of order n minus alpha. We have already defined what is integration of order alpha. Integration of alpha. So instead of alpha, here you have n minus alpha. So if we apply here, same definition we are using, same formula we are using. So we will get 1 by gamma of n minus alpha integral a to x, x minus t to the power n minus alpha minus 1 f of t dt. Now this is a constant term, so it can be written as 1 by gamma n minus alpha nth derivative of integral a to x f of t dt by x minus t raised to alpha minus n plus 1. So I have just taken this term to the denominator. Okay, so the power becomes alpha minus n plus 1. So this is a formula for Riemann-Liouville fractional derivative. Okay, so LHS indicate alpha derivative of arbitrary order alpha, and the limits are a to x. So a to x. So of course x should be greater than or equal to a. Of a function f of x is equal to 1 by gamma n minus alpha nth order derivative. This is our usual derivative that we do in calculus, integer order derivative. Integral a to x f of t dt by x minus t to the power alpha minus n plus 1, where n alpha lies between n minus 1 and n. So this is the definition for Riemann-Liouville fractional derivative. Even though this is the formula for fractional derivative, you can see that integral is involved in it. Okay, so the fractional derivative has the additional property of getting the characteristic of the integral function. Okay, so that is the advantage of fractional derivative. You know, the ordinary derivative, one of the most important properties, locality property. That is, the ordinary derivative is local in nature. It depends upon the values which are very near to it. But the fractional, when you come to the fractional derivative, the derivative itself has the integral property also. So this is a non-local. The fractional derivatives are non-local in nature. So it may include some additional property, because since the limits are there, so when we model some problems, some physical conditions or some complex problems are modeled, in them some additional properties will be there, some initial condition or some boundary conditions, etc. will be there. That can be incorporated in the fractional derivatives. So we have that provision is there for incorporating those additional conditions in fractional derivatives, but it is not there in the ordinary derivatives. Because in ordinary derivatives, it is a local one. So it depends upon the values which are very near to it, and we cannot incorporate the initial or some extra conditions which occur in reality. So in reality, there will be some restrictions will be there, or some additional conditions will be there. So that can be incorporated in the fractional derivative. So that is the advantage of it. So this is the definition of Riemann-Liouville fractional derivative. This derivative also has some limitations, and practically this integration is sometimes it is difficult to find out. The integration is also very difficult. So for overcoming that problem, another integration was integration was developed. It was developed by Capiccio. It is called the Capiccio fractional derivative. Now, the only difference is that here this is the Riemann-Liouville fractional derivative. Here you have, outside the integral sign, you have nth order differentiation. Now, in the Capiccio derivative, the only difference is that this nth order differentiation is taken inside the integral sign. Okay, even though they are not equal. So in that way, Capiccio derivative is defined. This nth order derivative is inside the integral sign. So you see the definition. It is, so this is the LHS. Again, there are some notations. You need not be frightened by seeing the notation. So they simply mean this is d to the power alpha. So it is the fractional derivative of order alpha. Limits a to x. And here we have c. It represents the Capiccio fractional derivative. This is for Capiccio. Capital C is also written here. So Capiccio derivative of fractional derivative of order alpha of f of x is given by 1 by gamma of n minus alpha integral a to x. So same definition. Okay, but here you have the nth derivative of the function. This is the ordinary derivative. Okay, nth derivative of the function t by x minus t to the power alpha minus n plus 1, where n minus 1, where alpha lies between n minus 1 and n. That is, the fractional order lies between n minus 1 and n. For example, if you have the fractional order lies, suppose the fractional order is 0.2. Okay, so the fractional order lies between 0 and 1. Then this definition becomes, so n becomes 1 here. Okay, so this definition becomes 1 by gamma of 1 minus alpha integral a to x, and here n becomes 1, so it is first derivative of it, f dash of t dt by x minus t to the power alpha, because when n is 1 get cancelled, so x minus t to the power alpha. So fractional derivative, practically Capiccio derivative is more applicable, and the main advantage is that if you find the derivative of the constant function, it happens to be 0 in Capiccio derivative, unlike the Riemann-Liouville fractional derivative. In Capiccio derivative, the derivative of the constant function is 0. Now, the properties of derivatives and integrals that we have for integer order need not be same with the fractional order. Okay, so in each definitions we have to check whether the given definition follows those properties, that is whether they have linearity properties like that. For example, the Riemann-Liouville fractional derivatives and integrals both are linear in nature. Okay, so that is d to the power alpha of function c f of x happens to be c into fractional derivative of alpha of f of x. And again, the second one is d to the power alpha of f of x plus or minus g of x happens to be the sum of their fractional derivatives. So these two properties, this is very easy to check. We have to just substitute in the definition of Riemann-Liouville fractional derivative, and this will come directly. Okay, so these results are very trivial. So both are Riemann-Liouville fractional derivatives and integral, both are linear in nature. Also, we have that zero rule is there, that is derivative of order 0 happens to be the function f of x also, f of x itself. Also, product rule is satisfied, that is product rule, we know what is the product rule for differentiation. That is also satisfied by the Riemann-Liouville fractional derivatives. Now, next is the composition rule for Riemann-Liouville fractional integral. This is a very important rule. So actually this represents integration of a fractional integral, that is fractional integration of a fractional integral. Okay, now I hope the notations are all clear to you. So first we will see this. What is this notation? It represents d to the power minus beta. So this represents integration of arbitrary order beta from a to x. Now again we are operating it with d to the power minus alpha. Again here you have integration. Same limits a to x. Now this happens to be d to the power minus alpha. So here first we are integrating of order alpha and then of order beta. And this happens to be d to the power minus alpha minus beta, provided this term exists. Okay, so this is actually integration, fractional integration of a fractional integral. So this term is a fractional integral, and again we are finding its fractional integration. So we can say in usual calculus we know what is a composition rule. So it is, we can say this is the composition rule for Riemann-Liouville fractional integrals. So this rule is satisfied. So if you have this minus alpha minus beta here, so here you will get the order to be minus alpha minus beta, and here alpha and beta are positives. Next important rule is the fractional differentiation of a fractional integral. So as I told earlier, all the composition properties need not be true for all derivatives, all fractional derivatives. Okay, that is the properties which we have for integer order differentiation and integration need not hold for fractional order differentiation and integration. So in each case we have to check. So here we have fractional differentiation of a fractional integral. So this is a fractional integral, a d to the power minus beta. So here minus is there. So this represents integration of order beta of x. Then here you have d to the power alpha. So d to the power alpha represents differentiation of order alpha. And this happens to be d to the power alpha minus beta a to x, provided here also alpha and beta are positive. This is very important here, because here if alpha is negative and beta is also negative, then this need not be true. So here alpha and beta both are positive, the function is continuous, and this RHS must exist. Then this composition rule holds. That is the fractional differentiation of a fractional integral. This is a fractional integral, and then we are differentiating it Also, it is a fractional differentiation. This is satisfied. And one of the trivial result is, suppose here alpha and beta are equal. So if alpha and beta are equal, what we will get? So you'll get the limits are same, a to x, the limits are same in both cases. So if alpha and beta are equal, we will get d to the power alpha, ax, then again d to the power minus alpha, f of x, and this is f of x itself. Okay, so here alpha plus minus alpha, you can use this rule. Alpha plus minus alpha is f of x, where alpha is greater than or equal to 0. So this is a very, we can say this is a trivial result in ordinary calculus, but not here. Okay, so all fractional derivatives need not follow this result. For example, if you take first here, if you take integration here, the result need not hold. That is, if you take d to the power minus alpha and then d to the power alpha, then it need not be equal to f of x. So that is the difference here. Okay, so this represents differentiation, and here you have integration. So the formula which we have the result for fractional differentiation of a fractional integral. This is a fractional integral, its fractional differentiation is there. And this is not true. That is d to the power minus alpha and then d to the power alpha f of x need not be equal to f of x. Its proof is also available. So what we have to understand is that the properties which we are thinking that they are true and will naturally hold in calculus, ordinary calculus, need not hold in fractional calculus. So the in each definition, actually there are many definitions are there for fractional integrals and derivatives, and each definitions has its own properties. They have its own properties as well as their own limitations are there, as well as advantages are there. Now next we will see some problems. So now we will see how to apply this using this definition. We will see how to do some problems. So for doing the problems, I will just make a notation I for integration. Okay, so this capital I is same as d to the power minus alpha. So for just doing the problems for the sake of simplicity, I am using this notation. D to the power minus alpha is notated by the capital I. So this is 1 by gamma of alpha integral a to x, x minus t whole to the power alpha minus 1 f of t. So this is a definition of fractional integral of arbitrary order. Now suppose our problem is to evaluate the half integral of the function x cube within the limits 0 and 1. Okay, so the function is x cube and you have to find the half integral of order half. So again we can substitute in this formula. So here alpha is half here, alpha is half. The function f of t will become t cube, and if you substitute here, what you will get is 1 by gamma half. So this is gamma half. Integral limits, here the limits are from 0 to 1. So 0 to 1, x minus t to the power alpha minus 1. So half minus 1 will become minus half. F of t, the function is t cube dt. Now here sometimes the integration will be difficult, but here x minus t whole to the power minus half t cube. Here we can use the beta function. That's why beta functions are important. We can write minus half as half minus 1, and 3 we can write it as 4 minus 1. So this is in the form of a beta function. Okay, x minus 1 to the power y minus 1. So this is nothing but beta of 4 comma half. So this is the I have already given the definition of beta function. So this is the definition of beta function. So here this integral whole value. So we have 1 by gamma half beta of 4 comma half. So we got the answer in terms of beta function. Now I have already mentioned the relation between beta and gamma function. So beta xy is nothing but gamma x gamma y by gamma of x plus y. So here if we substitute here, we will get 1 by gamma half. So this is gamma 4 gamma half gamma of 4 plus half. Now we know gamma 4 is 3 factorial, gamma half get cancelled here, and gamma 4 plus half. 4 plus half is gamma 9 by 2. We can use the inductive formula here. Okay, gamma n plus 1 is n gamma n. Repeatedly we can use, and at last it will reach to gamma half, and gamma half is root pi. So if you do some calculations here, you will get the answer. So in this problem, you can see that we have used both beta function and function. Now we will see the next example. So suppose we want to evaluate the 1.5th derivative of a function f of x, and the limit are from 0 to x. Okay. So again, this here we will make use of the formula that we have already studied. Okay, so I told that this 1.5 can be written as 2 minus 0.5. So we can write this as d square d to the power minus 0.5. Now suppose that for simplicity, so suppose f of x is 1. Then 1.5th derivative of 1 happens to be d square. Then here you can see here you have the integer derivative. D square is the integer derivative, and here you have the fractional integration. Okay, because here minus sign is there. So it represents fractional integration. D square is the ordinary derivative that we have studied in calculus. So it becomes d square d to the power minus 0.5 of the function 1. For simplicity, I have taken the function 1. So this becomes d square d to the power minus, I have just denoting it by the capital I 0.51. Now we are using the definition of integration here. So this become integral of this is 1 by gamma half. Here you have alpha is 0.5. So gamma 0.5 integral 0 to x. They are the limits. X minus t to the power alpha minus 1. So it is half minus 1 minus half dt. Now here you have integration which you can do it very easily. This is 1 by root of x minus t. Integrate it, put upper and lower limits. This is very simple to do. And substitute the value of gamma half is root pi. Now here you have the ordinary derivative 2 times. Okay, so first you have to differentiate root x. So we'll get 1 by 2 root x. Again you have to differentiate it again. So this fractional integration becomes very easy if we adopt this method. Okay, so here we have we had the 1.5th was the order of differentiation. It was a fractional derivative. So what we did is we split it into 2. We can split it in the any way, but it should satisfy the condition. Okay, so earlier I told that some properties are valid in some derivatives only. So that condition you have to check. We cannot split it arbitrarily. We can also write this 1.5. We can also write it as 1 plus 1.5. There is no problem. Okay, but we have to see in which the integration in some splitting, the integration will not be that much easier. Okay, so here I have split it as 1.5 as 2 minus 0.5. So this I have the advantage of this is the ordinary derivative and this is the fractional integral. So in this way we can use many technique, but this property should be valid in the corresponding definition or in the corresponding whatever fractional derivative we are using, that should satisfy this property. Then only we can split it in that way. Another example is this. Suppose we want to evaluate d to the power minus 1.5. Again, minus 1.5 from the limit a to x f of x. So here given an example, f of x can take any value. The limits, I have taken the general case, the limits can take any value. Okay. I just want to tell what about the order only. Okay, so the order is here minus 1.5. I am splitting it as minus 1 minus 0.5. Now this can be done. We have the property. Okay, using the composition rule, we can do this. So here what we're getting is d to the power minus 1 is the actual integration. That is the integer order integration. So for the integer order integration, the limits are not required. So we need not write limits here. But here we have a fraction. So in the fractional order integration, limits are required. So I have written here a to x. So this is the usual integration integral. And here you have the fractional integral, integral a to x 0.5. So what is the use of this is that even if we have the fractional integral of 1.5, 2.5 or any value, it is enough if we know how it behaves in the interval 0 to 1. In effect, only that will matter. Okay. So this can be written like this. This is the integer derivative, and depending upon the function, here I have not written the function. I have written only the operator here. So the operator can be splitted like this, and whatever be the function f of x, a to x, we can proceed like this. Similarly, you consider the next example. We have d to the power 3.2 limits a to x of the function f of x. Again, 3.2 can be written as 3 plus 0.2. Here also no problem. This property is satisfied. Now d to the power 3 is the ordinary derivative. So here limits are not required. It is the usual third derivative of the function. Here you have the fractional derivative 0.2 of order 0.2, and here we have the limits. So once you substitute the limits, and if you have the function f of x, we can evaluate the fractional derivatives and integrals using this method. Now, another important question is why we are using this fractional calculus. What is the advantage of this? So actually, fractional calculus is the generalization of the calculus that we have already studied. It is a generalized version, because in the ordinary calculus, here there n can only be an integer. In fractional calculus, n can take any arbitrary value. And some of the important reasons why, what is the significance of fractional calculus is, one of them is that it describes the complex phenomena in a very better way. That is, fractional calculus is used to analyze the behavior of nonlinear systems. As you know, in nature, majority of the systems are nonlinear, and we model it. When we model it, the differential equations, when we model it using the ordinary differential equations, it will not give the correct solution. In such context, fractional calculus are important. So in many cases, classical calculus is not able to describe the complex phenomena. So when the phenomena is nonlinear, the ordinary calculus is unable to capture that behavior. So practically, a situation described in terms of fractional derivatives gives a better fit to the actual data as compared to the integer order derivative. So, so in the class, I have described what is a fractional derivative and what is a fractional integral. Similarly, a differential equation which contains fractional derivatives is called a fractional differential equations. So there are fractional differential equations as well as fractional differential, partial differential equations are there. Okay, so the thing is that they are able to capture the reality in a very better way as compared to the ordinary derivatives. Now, the second advantage of fractional calculus is the non-locality character. That is, the integer derivative of a function depends upon the values very near to the function. Okay, but that is not the case of a fractional derivative, because the derivative itself include integral. Okay, so that is the advantage of fractional integral. And the third very important, most important thing about fractional calculus is that it has a memory effect. So what is this memory effect? That is, some phenomena in real world has the memory effect. So in that case, the current state not only depends upon the time, but also on the previous state. That is, we need to store what is the previous condition in some situation. And this is not possible in case of integer order differential equations. And in this case, fractional derivatives plays a vital role. Okay, so it has the capacity to store the memory. So in such situations, fractional derivatives play a vital role and they are more effective. So for practically using or for modeling purposes, this is more important. Also, it has applications in various fields of science and engineering, and recently many research are going in this field. So the main references which I have used here is, this is one of the classic books in fractional calculus written by Miller and Rose. It is an introduction to the fractional calculus and fractional differential equations. This is very good book, and if you are doing, if you are planning to do some work or research in fractional calculus, you should have a copy of this book. This is the oldest book, and it has almost all the definitions in a very lucid manner. Another one is another book is by this is Fractional Differential Equations. This is also a very interesting book, and it gives many applications, very real world applications of fractional calculus. Okay, so in this class, I have attempted to give you a brief introduction to the topic fractional calculus. Many things, many problems are still open. Nowadays also it is open, like what will be the physical interpretation of differentiation of arbitrary order. Even though some research are going on, but still it is an open question. That is, if you say derivative of arbitrary order, what does this physically represent? Because we know when we say the derivative, first derivative represents slope, then second derivative, third derivative, we have the physical meaning. But what is the physical interpretation of a derivative of arbitrary order? So that question is still unknown, the exact physical interpretation. But it has applications. Mathematically, we are doing so many things, and earlier only mathematicians were interested in this topic, but now many many scientists and researchers from applied fields have started studying this fractional calculus and applying it in their problems. Okay, so I will stop here. Thank you very much.
Thank you, ma'am. If the participants have any questions, you can either type that in chat box or ask directly.
Hello, good morning, ma'am. Ma'am, actually, I have a doubt. You have said the difference between a Riemann and capital is the derivative is a zero, ma'am, in a capital.
Pardon?
If I apply capital derivative, then we will get a zero, ma'am, for constant answer.
Yes, yes, yes.
In a Riemann, it is not possible, ma'am. If it gives another value, means why we are considering that Riemann for all the derivatives, ma'am?
Actually, it is half derivative of the constant function. It is not zero in Riemann-Liouville integration. So in each definition, we will get different values. It need not be true. Okay, so what we know is only what we have studied. We will think that the derivative of constant should be zero because we know only the ordinary calculus that we have studied.
Yes,
okay, we don't know what will be the higher versions of it. Okay, fractional calculus are yet to be discovered and yet to be studied more. So it is a generalization of ordinary concept, ordinary derivative. So we are thinking that this should be like that, but we don't know what are the possible ways, other things which can be possible. But the interesting thing is that its application, and it is applied in many areas of science and engineering.
Ma'am, and also one more doubt, ma'am. Actually, I'm doing research on this fractional differentiation only, ma'am. I'm using a software
Okay.
MATLAB. Ma'am, is there any
Which
way
software you are using?
MATLAB, ma'am?
MATLAB. Okay. Yes.
Yes, ma'am. There is any possibility to do integration for gamma function, ma'am?
Built-in functions are there na? In MATLAB. Built-in
Yes,
functions
ma'am.
are already there,
I'm
or
using it, but it is not getting, ma'am. With that, I'm asking if you know means it will be helpful, ma'am.
okay, or you can use so according to your problem, because even if the built-in functions are there, it may not suit to our requirement, our research
Yes.
requirement. So whatever
Yes.
problem we are doing, it may not be suitable for it. So the best thing is you write your own code. That will be
Okay.
better.
Okay, ma'am. Thank you.
Okay.
Hello, ma'am. Hello.
Hello.
Ma'am, my name is Pijesh, and I want to know something about. Is there any drawback with RL derivative, this Riemann-Liouville derivative?
The main drawback is that what I told is its use application. That is, when we use it, it is not so easy to evaluate the integral.
Yeah.
Okay, so that's why capture derivative is used.
Yeah. Okay.
In real world problem, okay.
Yeah. You tell me.
In real world problem, when we do in applied field and all, so capture derivative is more useful, and the difficulty is doing that integration part and getting an answer. That is the main drawback.
Yeah. Okay. So it means that capital derivative is more easy to handle than RL derivative.
Yes, 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 yes.
Yeah, okay, fine. Ma'am, then one more doubt is that when we talk about properties of RL derivative, I saw that what is the problem if alpha and beta is negative in that the definition? The composition rule, ma'am, share that about in
Okay,
composition
I
case.
think you are talking about in which I said the it need not be equal.
Yeah, that we in the section of properties of
Okay,
RL
that is
derivative. Yeah,
yeah,
ma'am,
that is
told
first if
yeah.
we the thing is that first if you do integration and then differentiation, okay, d to
Yeah.
the power minus alpha, then d to the power alpha, that will not be equal. That you can verify it using you take any function. So that is the drawback of the definition. Okay, so the definition does not satisfy that. Okay, so when you do it, or you simply substitute, you give one simple function and you just find. Okay, it is
Yeah,
easy to find
yeah.
of order one, you just do. Take a simple function and do, you will find that they are not equal.
Yeah, okay, ma'am. Then I have one more doubt.
And one second, there is also a proof for they are equal. Proof is available in the textbook that I mentioned.
Yeah, ma'am, I'll try.
Miller by Miller and Rose. For equality, the proof is available.
Yeah, I'll go through it. Is there a PDF available in Google?
No,
Or
for the first text, it is not available. For the
yeah,
second
okay.
text, it is there.
Yeah, okay.
First one is very rare book. It's
Yeah, ma'am. Okay, okay. And one more doubt is I have a doubt about capital derivative. In finding the solution of fractional derivative equation using this capital derivative ideas, I saw that always use open interval 0, 1. Can you give some? I don't know how why it's used open interval. Is there any particularized
for integration.
reason?
For integration, it does not matter now whether you use open or closed. It does not matter
Yeah.
because endpoints don't depend upon it. Now, so for integration, it does not matter.
I'm sorry, I didn't get you clearly. Means
As you are talking about the case of fractional integral.
yeah, in capital cases, finding solution of actual differential equation, why we find only on open interval 0, 1? Is there any particular reason for that?
Finding solution for which equation?
while finding solution for a fractional differential equation,
Fractional
why
differential, okay.
why
So
we
I have
find
not
only
so I have not discussed the fractional differentiation or integration. I will just give a thing that when we are doing integration, whether it
yeah.
is a closed interval or it is an open interval, it does not matter.
Yeah,
Okay,
okay.
so that's the reason. Or if there is anything in the definition that I have to see.
Yeah, okay.
I think that
So
will be the
it
reason.
does it doesn't matter whether it is open interval or
Yes,
closed interval.
yes, because if you are using integration,
Yeah,
if there is anything else is there, I have to see it.
yeah, ma'am, I will go through it. And can you just explain the memory effect and about
I,
applications?
Actually, it is the applied area that is in situations where human considerations are made. That is, we are choosing the second thing based on the first one. So the first one should be saved somewhere. So
Yeah,
based on that only, we will depend upon, we will decide what will be our second choice. Okay, so that storing effect is there. That is called the memory effect. So it is usually in the application problems only. So in the real world problems, when we are doing it, we come across such things.
yeah. What is the role of fractional differential equation, fractional derivatives in the case of memory effect, ma'am?
That's what I told, that the memory effect is not supported by the ordinary derivative.
Okay, okay,
Ordinary
okay.
derivative does not have that capability for storing like that. Okay, so the
That means
fractional
to
derivative
capture.
has that.
That means to
Hmm.
capture the real
Yes, yes,
idea
yes.
about
That
memory effect. Yeah, okay,
yes,
fine, fine.
yes, yes.
Yeah, fine, fine, fine. Yeah, okay, thank you, ma'am. It was nice class.
Okay, okay, thank you.
Hello, ma'am.
Yes.
Yeah, ma'am. There is so many derivative like such as RL derivative, capital derivative, Attagana Bologna, capital Fabricio. So, which derivative
Yes.
give most accurate solution, ma'am?
Actually, there is nothing like accuracy, but it will depend upon which problem you are working. Okay, so your problem will decide, or your research area, or whatever problem you are working on it. Based on that, you have to decide which integration or differentiation has to be chosen. Okay, so for that, some more study is required. This, what I told, is very basic thing only. So it's not that this one is good or that one is good like that. So if you are working in signal processing or in physics area, or what, it differs from area to area. Okay.
Yeah, ma'am. Suppose someone is doing in capital Fabricio and some other is working the same problem in Attagana Bologna. So, what's the novelty of that problem? Because the same problem, some other persons on Attagana Bologna, some other is on capital
Okay,
Fabricio.
okay, okay. So I understood you. So our main interest is not of getting the same answer going through different definitions. What is our concern is to find a solution to our real life problem. So whatever real life problem we are modeling it and we are using it. You are using fractional derivatives. So which definition will suit our physical concept? That is important. Okay, both will give different answers. That doesn't matter. Our aim is to solve a real world problem. For that, whichever is necessary, that we have to use.
Okay, okay, ma'am. Ma'am, one more doubt, ma'am. What's the peculiarities of
Yes.
Hilford fractional derivative, ma'am? Compared to
Which
other
one?
Hilford fractional derivative.
I have not seen that fractional derivative. It represents what?
Yeah, that I don't know, ma'am. Actually, I think it's a generalization of RL derivative, but I don't know much more about the Hilford.
Okay, okay. That we have to study in detail more. I have not seen.
Okay, ma'am. Okay. It's a nice
Oh,
section, ma'am. Thank you so much, ma'am.
okay, thank you.
Good morning, ma'am.
Good morning.
Ma'am, how can we connect fractional derivatives and fractals?
Yeah, in fractals also you have the concept of this this dimension is integer, non-integer values are coming there. Okay,
Yes,
so
yes.
I have not seen exactly how it is used, but I have seen that it has application. Fractional calculus is applied in fractals. So if you are doing research in fractals, you can give more specific answer to it.
Okay, thank you, ma'am. It was a nice session.
Okay, thank you.
Any more questions? Okay, I have put the feedback form link in the chat box. Please fill the details, your name, designation, and name of the institution carefully. If there are no more questions, I think then we can wind up the session. Okay. Hope there aren't any more questions.
Hello, ma'am. Hello.
Hello.
Hello, ma'am. I have one question.
Yes.
How we want to find the mild solution in fractional differential equation? What is the difference between mild solution and a classical solution?
Okay. In which context you are saying it?
Sorry, ma'am.
In which context you are saying it? What is your area or which?
In fractional differential equation.
Okay. Now you are applying it to which type of problems, like in physics or in any particular area where you are applying it?
Like physics or engineering mathematics.
So the thing is that the fractional derivative, or when you model this real problems using these fractional derivatives or integrals, they are able to solve it in a better way. So the capture derivative is mainly used in engineering and physics. Okay, so that will give a better result. But the thing is that the ordinary derivative is not able to capture some properties which there exist in reality. Okay, so it depends upon the problem that you are doing, what the extra condition you have, some boundary conditions you have, some initial conditions you have, or whatever you have, and you want that to be incorporated in the problem. So when you are doing in an ordinary derivative, you don't have that criteria, you don't have that provisions to include all those things. But here those extra conditions like some boundary or some initial condition or effect of some other parameter when the parameters are changing or some other effect are there, you are able to capture it and you are able to use it in this fractional derivatives. So that is the main advantage of using it.
Okay, ma'am.
Okay, thank you.
Okay, thank you, ma'am.
Hello, ma'am. Can you explain the geometrical interpretation of this fractional differential equation?
That's what I told in the last class, in the class itself. That is even though a little bit work is done, but the exact geometrical interpretation or what will the derivative, fractional derivative, when alpha is arbitrary, that is still an open question. Okay, in some cases there are some works are done and some theories are there, but what is generally what does it represent when alpha take any arbitrary value? That is still an open question, and many of you can work on it.
Okay, ma'am. Thank you. Nice class.
Okay, thank you. Okay, thank you.
Hope there are no other questions. It was such an informative class, Vijitha Miss. So on behalf of Department of Mathematics, St. Mary's College, Thrissur, I would like to express our sincere gratitude to you. Next, I would like to thank our principal, Dr. Sister Maggie Jose, for the support given in organizing this webinar. Finally, I express my sincere thanks to all dear participants for your presence. Thank you.